today, in a sense, we should have done some of what we're going to do today earlier. What we're going to do today is more important than nomenclature because it's related to how you encounter molecules in your everyday life. Things that you taste, things that you smell, things that you cook with, things that you experience. And I may be the last person at BYU who's going to tell you about this if you're not going to take more chemistry classes. So I feel like it's important not because anybody on the MCAT is going to ask you what does a carboxylic acid taste like, but because you're going to cook with vinegar in the future, and I want you to know a little bit about the chemistry. So this is sort of education for your life. And I'll help you as we go along to figure out sort of exactly how I might ask test questions about this. You've learned, did I press record? Yes. You've learned about carboxylic acids. You should know how to recognize them as functional groups now. Carboxylic acids have a characteristic taste, and then depending on their size, they have a characteristic smell. So in general, the taste is sour or tart or tangy. So anything that tastes sour or tart or tangy probably has a carboxylic acid in it. So the classic example is vinegar. This is acetic acid, and you can use this in cooking, sweet and sour sauce, salad dressings, whatever, lots of different kinds of vinegar. But they all have this carboxylic acid in them, and that's the sort of tart taste. Another carboxylic acid that's found frequently in fruit, particularly citrus fruit, is citric acid. No surprise at the name there. This is, and I don't want you to memorize the structure of citric acid. I'll make you do that in 352, but not today. This is citric acid, and it's found in lots of different fruits, but also especially in citrus. So the sour taste of lemon, lime, grapefruit, oranges is citric acid. And if you like sour candy, like Sour Patch Kids, probably some of that crystalline stuff on the outside, in addition to the sugar, is probably some citric acid. You can use citric acid as a preservative when you're canning. You can buy it from the canning section at Macy's. I think Utah is the only place where the grocery store has a canning section, but one time I decided I was going to can some tomatoes. The only one time I ever did that, and I had to buy some citric acid. I'm like, I wonder how that tastes. And it was like, oh, it's sour. Yep. I mean, no surprises there. But that is the taste. And so when on the Great British Baking Show, when Paul Hollywood's talking about how that fruit really adds the acidity, he's talking about the citric acid, the vinegar that's added. That's tartness. Okay? Now, as molecules change in shape, sometimes their smell changes. Vinegar has a characteristic smell. It's not particularly unpleasant, but in high doses it can be somewhat overwhelming. It gets worse as the carboxylic acid increases in size. So behold, butanoic acid, 4 carbons. A non-systematic name that's related is called butyric acid. And these sort of intermediate molecular weight acids smell like vomit and sweaty feet and also Limburger cheese. So a lot of the so-called stinky cheeses, which actually some people like eating, have these kinds of molecules that give them the characteristic aroma. I'm going to show you just a few. We won't worry about their names, and we won't worry about which context one molecule is present in versus another. These are all types of molecules that can be found in various amounts in the smells associated with these things. So, and understand that for something to be smelly, for you to smell it, it's got to be volatile enough to get into the air so that it can get into your nose. And it is interesting that your nose is sensitive to changes in structure, right? Vinegar smells different from vomit. which is why we use vinegar in things that we eat instead of not using it, I guess. Also interesting is if the carboxylic acid gets many carbons long, so let's say 2, 4, 6, 8, 10, 12, 14, 16, 18. This is something that you could use as a soap. This is called a fatty acid. It's called a fatty acid because it's a carboxylic acid that you can isolate from fats or oils. And this is an example of a saturated fatty acid which has no, and by saturated I mean no pi bonds. We'll have some more to say about saturated fatty acids a little bit later, but you can see there's a continuum here. Intermediate molecular weight carboxylic acids smell like vomit. Short ones aren't so unpleasant in general, they taste sour. And then the long chain fatty acids are possibly useful as soaps for reasons that we'll talk about a little bit later. So as an example, kind of question you might experience on an exam, a bunch of structures, which of the following tastes sour? And you choose the carboxylic acid, right? Not that hard. Okay, let's now talk about esters. Esters are kind of fun because unlike the intermediate molecular weight carboxylic acids, esters have a characteristic smell that is generally fruity or floral. So a lot of molecules that smell pleasant to us are actually esters. You've seen the structure of an ester. It has a carboxylate carbon, but the oxygen, instead of being bonded to a hydrogen in a carboxylic acid, is bonded to another carbon. This portion of the esters can be synthesized from precursor molecules, and the two precursor molecules are a carboxylic acid, which contributes that portion of the ester, and then an alcohol, which contributes this portion of the ester. So when I talk about esters, I'll talk about the alcohol portion and, the carboxylic acid portion. The overall, the reaction that generates these two is called a condensation reaction because you lose water. So this R group and this oxygen end up in the ester, but the proton and the OH group are lost as H2O in the reaction. That's something you'll learn about in 352, and you'll actually do if you take you'll do this reaction if you take the organic lab 353. Now, esters, as I said, have characteristic smells, and particularly the low molecular weight esters are floral or fruity. I'll just give you a few examples. This one smells like cherries. If you change the structure, you get a different smell. So here you can see, comparing these two, that the carboxylic acid portion is different, and the alcohol portion is also different. And you can see it is interesting that your nose is sensitive to that small of a structural change, because you know the difference in smell between cherries versus apples. And this highlights a really important principle in organic chemistry, which is structure and shape are related to function and properties. You change the structure, move methyl groups around, add carbons, you change the properties and the function. That means there are receptors in your nose that are sensitive to those minor differences in shape. So what an amazing creation the nose is, right? That we can detect very, very small differences in molecules. It took humans how many millions of years to develop? We'll learn later in this class. We have analytical tools called mass spectrometry and NMR spectroscopy where we can sense differences between molecules. It took us so many years to build those molecules, And creatures have been smelling things on this earth for many, 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 many more millions of years than that. So the nose, what an amazing creation. Now, how might this show up on an exam? Oh, I want to give you another one. Some of you may have actually done this reaction in high school, depending on your high school chemistry class. Sometimes they'll have you, the reaction's pretty easy to do. The reagents are pretty inexpensive. It's pretty safe to do, and you get to make a lovely smell. This one's banana. Now, how might you see this on an exam? I'll say, which of the following smells like banana? And then there'll be like 20 different esters, and you'll have to, no, I know that's not funny to you, so I apologize. No, you'll just choose the ester, right? Choose the low molecular weight ester. Now, if you want to get really into this, Google ester fruit smells, and there is an infographic that has on this side a list of carboxylic acids and on this side a list of alcohols, and you mix and match them to make various esters, and some of them smell like raspberries or apples or citrus or mango or almonds or a bunch of other things. You can delve into that. We don't care at that level, but I just want you to recognize, oh, of the weird molecules shown, probably the ester is the one that smells like fruit. Yes?
Do they taste like fruit too?
Do they taste like fruit too? I don't know. I would say probably that's a question for the food scientists and neuroscientists out there. Taste and smell are related. Like the smell that you experience can also influence the taste, like the perceptions are related. So I don't know if you drip an ester on your tongue and you're like, does that taste like banana? Probably because your nose is telling you, hey, that's banana. I don't know. Good question. All right. Okay, another ester that's related to foods that is pretty important that we'll talk about a ton more is esters that are present in fats and oils. So, behold, the more complicated name for fats and oils are triglycerides. The triglyceride is a triester. It has an alcohol portion that has 3 oxygens, 3 carbons, and each carbon is bonded to an oxygen. And then attached to each of those oxygens are long chain fatty acids. So we'll just do 16, 2, 4, 6, 8, 10, 12, 14, 16. And this, of course, is the carboxylic acid portion. Now, I'm going to do something that those of you with pencil and paper can't do, so you're going to hate me for that, but we need time, so I don't care that much. You already hated me anyway, so this isn't actually going to move the needle. There we go. So that's a triester. And this is an example of a saturated triglyceride. Now, the difference between fats and oils in general, fats come from animals and oils come from plants. But they all have this basic triglyceride structure. The orange portion is called glycerol or glycerin, and then the blue portion that comes is called the fatty acid portion. And nature actually makes this from glycerol and from a fatty acid. You'll learn about that in 352. This is an example of a saturated triglyceride because there are no double bonds in it. Let's talk about an unsaturated fat. And yes, go ahead.
Do all those carbon chains, do they have to always be identical?
No. Do all the carbon chains have to be identical? They don't. And so nature mix and matches them. They can vary in length from like 10 to 12 to 18 to 20 carbons, and they can vary in whether or not there are double bonds. And I don't know how nature controls what goes where. And in general, if you have a bottle, and we'll talk about this probably next time, but if you have a bottle of olive oil, they can tell you after the fact by analysis about how much of each kind of fatty acid is present, but they probably can't tell you at any one time which triglyceride has which fatty acids because it's heterogeneous. There's just a mixture. Yeah. So as an example of that, let's draw a monounsaturated fat. So Here, the double bond will be between carbon 9 and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the double bond is between 9 and 10. And in unsaturated fats / oils, the double bonds are always cis. Nature makes them that way, and that has some consequences that we'll deal with later. So 9, 10, 11, 12, 13, 14, 15, 16. All right, so that's a double bond between carbons 9 and 10. It's in the Z configuration. The reason we call this unsaturated is if you compare a regular fatty acid, you'll see that 2 adjacent carbons have as many hydrogens as possible. They are saturated with hydrogens, whereas the one with the double bond has fewer hydrogens than are possible, and so we call this unsaturation. So this is an example of a monounsaturated fat. You will see that on food labels, and of course polyunsaturated fats or oils would be multiple double bonds. Okay? Now, still on the theme of structure and function and properties being related, you will see, probably not today, probably next time, how inclusion of the double bond changes the properties of the molecule. But here's a preview. Saturated fats tend to be solids. Fats with even one double bond in them tend to be liquids. So your vegetable oils, your olive oils, your liquid oils, those are all have majority unsaturated triglycerides. Whereas your bucket of Crisco or your big bucket of manteca from the HEB in South Texas, that's where I serve my mission, right? And tamales made with actual lard are fantastic, except no substitutes, but that's saturated triglycerides. Okay. We should tell you about omega-3, shouldn't we? Yeah? Okay. So you've heard about omega-3 fatty acids. What on earth are they talking about? I'm going to copy this triglyceride structure, and we'll show you the structure of a polyunsaturated triglyceride. So in some fatty acid portions of a triglyceride, there are multiple double bonds, and the double bonds are usually separated by one carbon. So the next double bond here would be between carbons 12 and 13, and then another one between, another one between 13, 14, between 15 and 16, and then we'll go 17 and 18. So this is an 18 carbon fatty acid. You will see this described based on the number and location of the double bonds. And some of these fatty acids have non-systematic names, because who wants to figure out how you name an 18 carbon chain? So I think this particular fatty acid is called, I think it's linolenic acid. You don't need to know that. You may see it if you're in food science. But this is an example of an omega-3 fatty acid. So where does the omega come from? It turns out that chemists often have multiple ways of talking about how far atoms are apart from each other. You could say these two atoms are bonded to each other, so that's position 1 and that's position 2. Or this one's on carbon 1 and this one's on carbon 4, so that's a 1-4 relationship. Another common way is to count location relative to a point of interest. So for a fatty acid, the carbonyl carbon, the one that's from the carboxylic acid, is the point of interest. The carbon that's adjacent to that one we call alpha. A is for adjacent, but we use Greek letters, so that's the alpha carbon. The one that's adjacent to that one is called the beta carbon, and then we just keep counting upwards with Greek letters until we no longer know them. So we're there, alpha, beta, gamma, delta. I happen to know that the next one is epsilon, so yay for me. But at that point, we sort of run out. There are other Greek letters, but who knows? So then and we might have run out anyway before we got to the end. So sometimes we skip to the end and we start there. And the last letter of the Greek alphabet is omega. And that you should at least be familiar with because one of the titles of Christ is Alpha to Omega. Alpha and Omega, the beginning and the end, everything. And so the omega end of the carboxylic, the fatty acid, is the last carbon, right? And then if we count in from the last carbon, 1, 2, 3, third from the end, there's a double bond. So an omega-3 fatty acid is one which has a double bond on the carbon that is third from the end. All right? Yes?
And it doesn't necessarily have anything to do with the amount of double bonds. So if you had more than this.
So it doesn't necessarily have to do with the amount of double bonds. For example, these two may not be present. There could be an omega-3 fatty acid that would have this one, but not these two. So to describe something as an omega-3 fatty acid just means there is at least a double bond in that place. Yeah?
You said an omega-3 fatty acid had a double bond 3 from 10?
Yes. Right now, so there are multiple kinds of omega-3 fatty acids, but that's where the term comes from. Yes?
What about like omega-6? Is one, right?
Yep, so you will, less commonly you will hear about counting from the end, 3, 4, 5, and 6. This is also an omega-6 fatty acid, yeah. So you'll sometimes hear those terms too. Now, yes, go ahead.
So for that one, would it be omega-3, 6, whatever the next one is?
That would make sense. Could you describe that as omega-3, 6, I don't know, 9? I suppose. I don't know if anybody does. Now, what's the deal with omega-3 fatty acids? Consuming fats or oils, the oils that have omega-3 fatty acids in them, is associated with positive cardiovascular outcomes. We're talking about lower cholesterol, lower LDL, which is related. If you have lower LDL, then that's better outcomes in terms of avoiding cardiovascular disease, atherosclerosis, and so on. I don't know the biological mechanism there. I don't know why consumption of the omega-3 fatty acid tends to lower LDL. And so that's a subject you'll have to learn from somebody else because I just don't know. But as you know, anything that has a real or purported health benefit is then used as a marketing tool, right? So you can now go to the store and you will find products that say, omega-3 fatty acids, and it's like, so for example, if you see two bottles of olive oil, and one of them says, now with omega-3 fatty acids, and it costs like double the price, probably don't buy that one because the other one also has omega-3 fatty acids in it, so it is mostly marketing. Similarly, for example, eggs. You can buy eggs that are enriched in omega-3 fatty acids, and that may be a good thing, right, because of the positive cardiovascular outcomes. But actually, how are they getting that? They're just actually feeding the chickens a diet that is rich in omega-3 fatty acids, and then that's getting incorporated into the eggs. So when you see it as a food label, just be a little bit critically thinking. It probably is good for you to consume things with omega-3 fatty acids, but don't be conned into believing that there's more omega-3 fatty acids in this bottle of olive oil than in the other, because that's probably not true. Okay, that's probably enough on that. We have more to say about fats and oils in a little bit, but we'll come back to that. We want to now talk about, we've already talked about some unpleasant smells, so in the spirit of the Grinch, this is stink. We'll now move on to stank, and these are the amines. You've learned about amines. You've seen them act as bases. This is not a discussion of amine chemistry. It's mostly of how amines smell. So this is the simplest amine, ammonia. This is a household chemical. You probably encountered it before. The smell is, I don't know, how would you describe it? Like ammonia? Yeah. It's pungent, I might call it acrid, it's unpleasant, and you almost wish you didn't smell it, right? Like it makes your nose feel, I mean, I would describe it as nose hair curling, but I don't know that that's makes sense to anybody. Anyway, it kind of is just ick. There are other amines that smell worse. So trimethylamine has 3 methyl groups instead of 3 hydrogens. And this smells like fish. So the characteristic fishy smell is from trimethylamine and other low molecular weight amines. For example, if we did, I suppose I can just do fishy, right? Everybody gets that? Okay. If we added carbons and these were ethyl groups, triethylamine also smells fishy. So there's an interesting story there. If you were to go into a pub in Britain and order fish and chips, they would probably give you a small slice of fruit with your fish. What is the fruit they would give you? Lemon, all right? And people would squeeze the lemon over onto the fish. Now, why do they do that? Well, maybe they like the taste of lemon, and lemon is sort of a pleasant taste and a pleasant smell. But part of the reason is that the lemon contains citric acid, which is a carboxylic acid, and the fish has a fishy smell, and it is a base. And so what happens when you put lemon juice, when you squeeze lemon juice on fish, is at least some of the molecules that smell fishy act as bases and deprotonate the acid, at least some of the acid from the citric acid in the lemon juice, and the base gets protonated, becomes positively charged, the acid gets deprotonated, becomes negatively charged. This now ammonium ion that you've seen before is not volatile because it is charged, and it stays in solution near its counter ion, and so rather than it becomes part of air, rather it doesn't evaporate into the air so much as it stays in solution, so it's much less smelly. So one of the purposes of putting lemon on fish is not only to enhance the flavor, but also to suppress the fish smell. Now, why you would want to suppress the fish smell when you are on purpose eating fish is maybe beyond me. I don't know. I'm not necessarily a huge seafood person, but that's what you're looking for. And if you want to do an experiment, take you and a friend and go to the seafood counter at whatever grocery store, pick a fish that still has a head with eyes in it, and then wrap it in foil. And you've got 2 fish, right? You need a control experiment. You do the one where you squeeze out a lemon all over the fish, wrap it in foil, and then you're going to put that fish in the trunk of your car. And you need to do this soon because it's getting colder. And you shut the trunk and then just leave it out in the sun, and your friend's going to do the same. And in a week, I want you to see whose trunk smells worse. Probably your friend's, right? This is your assignment before general conference. You need to figure out the fish smell experiment. Okay, it gets worse because some of the amines smell like death. So these are literally breakdown products from certain amino acids. So as corpses are degrading, some of these molecules are made, and the name really says it all. 1, 2, 3, 4, 5. This one, 4 carbons with 2 amines, is called putrescine. And this one that has 5 carbons is called cadaverine. So that is the smell of rotting flesh. So if you happen to, I don't know, be in an unrefrigerated morgue, if you're a coroner and the power goes out, you need to go and get a lot of lemons, I guess, and then, okay, that wasn't funny. But if I were, for example, to ask you which of these molecules smells like zombies, you would choose the amine, okay? That's probably not how I'll ask the question. Which of these smells like rotting flesh? Although zombie sounds like a funner question. In the zombie apocalypse, what smell will you be smelling? Which of the molecules will you be smelling? All right. Now, that was stank. We got one more, and that is the stunk category. Stink, stank, stunk, da-da-da-da-da-da. Those are the thiols. And these basically smell like rotten eggs or skunk. Skunk stunk. So here are some molecules that are present in skunk spray. You've got 2 relatively low molecular weight thiols. And that's, when there's a dead skunk in the middle of the road and you can smell it. They're very volatile. It spreads out over quite a wide area. Their thiols do have decent uses, though, because we can detect the smell even at really, really, really low concentrations. So you may be familiar with the so-called smell of natural gas. It turns out that natural gas, propane or butane or methane, are odorless. They don't have a smell. But, and that was a problem in the early days of natural gas, because if there was a leak, you couldn't detect it until you lit a match and the whole place went up, right? So it became important to have some way to detect a leak, and the best way to do that, they found, was through smell. So now natural gases they add some smelly molecules to the natural gases, including these 2 thiols. And they don't add a lot, very, very small concentrations. But when you've lit the grill and it didn't light and you smell that smell, that's the thiol that you're smelling. And that indicates that the natural gas is leaking. The smell goes away when the grill is lit because the molecules get burned and oxidized and you don't smell them anymore. Now, not all thiols are unpleasant. There are some that we actually use in cooking, though the smells are controversial. So garlic and onion breath are generally unpleasant, but people like garlic and onion in their food. So fun in cooking, bad on dates, I don't know. This is a thiol that's present in onion. It's an interesting 2 sulfurs, and often part of the point of cooking garlic and onion is you saute them to break down the cell walls to start to release some of these flavor and odor type molecules, many of which are thiols. The one that's really common in garlic is not a thiol per se, but it has sulfurs in it, and I think it can break down to release thiols. So I'll just draw it here for you so that you've seen it at least once in your life. This is called allicin, and I suppose Utahns are always looking for alternative ways to spell names of children. So I already told you the name of your firstborn child from last time. It was that horrible molecule. What was it? Like 3-oxo. Yes, there it is. There's the name of your firstborn child. Butyl dimethyl dienoyl chloride. And the name of your second-born child is now allicin. Okay. Anyway, so sometimes we use these thiols as molecules for cooking in small doses. All right, we need to keep moving. I want to tell you about alcohols, and in particular, we're going to talk about polyols. These are alcohols that have many OH groups, and these are generally sweet. So an example is glucose. You don't need to memorize this structure. You will in 352, but for now, glucose, you can see, is highly decorated with alcohol functional groups. If you've ever tasted glucose, it's not as sweet as table sugar. So I'll actually draw the structure of table sugar for you, and you will see that table sugar has even more alcohol groups decorating it. Turns out table sugar contains glucose as a subunit, but it's bonded to something else. So I'll just draw that real quickly. Again, you don't need to memorize this structure, but you would need to recognize if I asked which of the following molecules are sweet, and you would just look for the polyols, the molecules that have multiple alcohols. And we're not going to push you too far on this, because I bet you somebody wants to know, well, how many alcohols do I need before a molecule becomes sweet? And the answer is, I don't know. So this is sucrose. Glucose and sucrose taste sweet. Glucose is a molecule that's the starting point for carbohydrate metabolism. You break it down into things that you can make ATP from. You'll learn about that in 352. Glucose and sucrose, though it's not clear now, are actually disguised aldehydes and ketones. And those are pretty reactive molecules, and that's why it's not good to have super high blood sugar levels. You'll learn about that more in 352 and other classes. Despite that danger, that doesn't prevent me from vigorously seeking out sugar to consume. There are some molecules that people have tried to develop that are not used in a metabolic way, like glucose is, but that nevertheless taste sweet. Here's an example. This molecule is called sorbitol. It's a polyol, but you'll notice that it lacks, it is not an aldehyde or a ketone, it's just a polyol. If you look at glucose or sucrose, it's totally mysterious why I'm calling them disguised aldehydes and ketones. Don't worry about that till 352. But this is sorbitol, and that's used as an artificial sweetener. There are trade-offs and benefits and disadvantages of various artificial sweeteners, but this is an example of one that's a polyol. Now, not all molecules that taste sweet are good for you. So here is a very short polyol. This is called ethylene glycol. If you've encountered it before, because it is antifreeze. So if you smell it, it smells kind of syrupy. It smells almost like corn syrup, but it smells like something's kind of off a little bit. And this is why antifreeze is labeled keep away from pets and children, because they don't know the difference. And so it'll taste good, but it's bad to consume. It's like dangerous for you. I don't know that it tastes good by experience. Yes?
Polyols are just more than one alcohol.
More than one alcohol, yeah. So if I ask which of these is sweet, look for the polyol. Yeah?
Do you know anything about aspartame? Is that a polyol?
Aspartame is not a polyol. Aspartame is two amino acids bonded to each other. I don't know the structure off the top of my head. I almost do, but there's actually a whole science of molecules that taste sweet, and not all of them are polyols. So presumably that's binding a particular receptor on your tongue that says,
Do you know why it's like bad?
Is aspartame bad for you? With all of these artificial sweeteners, there are pluses and minuses, and depending on where you get your information, there are people that are for them versus against them. I don't actually know any of the epidemiology. The one thing I know is people that have aspartame contains the amino acid phenylalanine, and there are some people that have a metabolic disorder called phenylketonuria, which they have a hard time metabolizing phenylalanine, and that is dangerous for them. Yep. Okay, let's see. I think, was that it? Oh, a couple more tastes. Need to hurry. So this is the boring one. The salty taste. What tastes like salt? Salt, yeah. Basically electrolytes, NaCl. Other electrolytes also taste salty, but it's thought that one of the reasons we crave the salty taste is because some protein sources, because muscle has a lot of electrolytes in it, protein tends to taste salty even without seasoning, and so perhaps one of the reasons we crave the salty taste is it's just a way of getting us to eat protein. Another taste that's on your problem set is the taste of umami. This is a taste you probably I didn't learn about it in elementary school when all the tastes were like salty, sour, sweet, spicy. But this is another taste, and that's umami. It's sort of a unique savory taste. And it's generally associated with a couple of molecules, but most commonly this amino acid, which paired with its counter ion is called monosodium glutamate. And I've shown this amino acid in the form in which it would exist at pH 7. This is MSG, if you've heard of that. And that's the sort of savory taste of umami. There's been some controversy over MSG, though I think the purported health issues are overstated. I think it's generally not considered to be an issue anymore. I could be wrong on that. So food scientists, you'll have to figure that out. Lastly, on our tastes, and this is not really a functional group thing. This is a unique molecule. So molecules that are spicy or pungent bind particular receptors. They're called vanillin, I think, vanillin-like receptors. They bind these receptors and they activate an ion channel that is interpreted in your brain as heat, even though it's not. So it's a kind of chemical heat in the sense that you feel like your tongue's on fire, but you measure the temperature and it's not. You're fine, right? It's purely a chemical thing. So the most famousest of the spicy molecules is capsaicin. You've probably heard about this. It's a pretty nonpolar molecule, which is probably why it doesn't necessarily help to drink a ton of water when your tongue is on fire from a spicy molecule. So this is the structure of capsaicin. It has all kinds of functional groups in it. And it's probably the portion on the left-hand side that's responsible for binding the receptor that makes you feel like you're on fire. This is an ether functional group. This is an alcohol functional group. This is an amide. Here's an alkene. So a nice grouping of functional groups. There are a few others. So this one is called piperine, and this one's present in black pepper. So when you salt and pepper your food, the little bit of spice that you're getting from the black pepper is because of this molecule. You can see that it is also relatively nonpolar. And then I'll show you one more. And these, there looks like there's maybe some structural relationship between capsaicin and piperine in the sense that they both have rings on one side and they both have some double bonds and they both have amides. There's another molecule that's associated with mustard and wasabi and horseradish. This is a really small molecular weight thing. It has a weird functional group that we won't even worry about, but if you want to know what gives mustard its particular smell, or wasabi or horseradish, it's this. So if I ask you which of the following is spicy, you need to look for something that looks like capsaicin. I promise not to ask you about that one. And I'm circling the small molecular weight one that's from wasabi that's weird. Okay, so that's your whirlwind tour through what things taste and smell like. I hope that's kind of fun. Now what we want to do is talk about non-covalent interactions, because aside from what things taste or smell like, this is going to be the one that most probably influences your day-to-day life. When we're done here, what we need to know is why oil and water don't mix. We need to know how bubbles form, why soap works to dissolve nonpolar molecules. We want to know why sodium chloride dissolves in water. All of these are issues that are discussed in your problem set. And I want you to know them mostly because I feel like you should be curious about the world around you. Someday you're going to be parents and a child is going to ask, "Mommy, why is the bubble?" And you're not going to know how to answer that question because it's not a sensible question. And you can't really explain that to a 3-year-old. But I want you to know why is the bubble, because you can understand it. All right, so to begin, we're going to summarize some things that I assume that you learned in general chemistry. We're not going to spend a huge amount of time on them. We're going to start in order of strength for non-covalent interactions. You have otherwise heard of these, also known as intermolecular forces. These are forces between molecules. And in order of strength, we're going to do ion pairs. This is basically Coulomb's law that opposite charges attract. So an ion pair is a sodium and a chloride being close to each other, right? Now, you probably called this an ionic bond. I would call it an ionic interaction. And these are relatively strong and they are distance dependent, meaning the closer the two ions are together, the stronger the interaction. And if you've learned about Coulomb's law, for the force between two ions, it's a 1 over r squared relationship. For the energy of the interaction, it's a 1 over r relationship. That means the shorter the distance between the two, the stronger the interaction is. Now, you learned probably in Gen Chem, oh, that ionic bond, it is so strong because if you put salt on a hot plate, you got to turn that thing up to like 3,000 degrees before the salt will melt. And that is true, but you put the salt in water and the ions fly apart. So how is that strong? You're going to see in OChem that strength is always relative to what? And the relative to what in this case as to why salt dissolves is an ion-dipole interaction. Now, an individual ion-dipole interaction is weaker than a single ion-ion interaction. A dipole arises because one atom in a structure is more electronegative than another. I assume I'm telling you stuff you already know. You're good on that? Hydrogen's less electronegative than oxygen. So you've probably seen a dipole drawn like this where the arrow draws towards the negative side, the plus is towards the positive side. Multiple water molecules can orient themselves such that the negative end of their dipole is oriented towards the ion. And in so doing, you can replace one strong ion pair with many weaker ion dipole interactions. And in that way, the water molecules can actually get in and separate the sodium and the chloride ions. You're going to see in organic chemistry that processes that are spontaneous are processes where the interactions that you form are stronger than the interactions that you break. So salt dissolving breaks an ion pair interaction, but it generates many more ion dipole interactions, which overall pay for the lost interactions that you lose. That's the general idea. Okay, I need one more day on this, so Monday we'll finish up on this. Wednesday we'll move on to chapter 4, and I'll adjust study guide due dates accordingly.